Okay. So, but before we enter into the timing closure part, I think it is important to understand some variabilities that need to be accounted for when we do timing closure. Okay. Raghav, is there anything else that is pending? I see your hand raised. Okay. So there are some uncertainties that we need to manage. Where could those uncertainties come from? They could come from clock generation. The PLL that is generating the clock, that could have some jitter in it, that could have some different delays across different time zones, whatever. There could be drift in the oscillator and so on. Then there are device variations. There are power supply variations. There are interconnect variations where you could have crosstalk between interconnects, and therefore when both the signals are rising, you have one kind of delay. When one of the signals is falling, you will have a different kind of a delay, and so on. There could be variations in temperature. There could be variations in loading of different flops or stuff like that, and so on. So there are many uncertainties that clock arriving at any flop would see. What we are saying is, see, यहाँ पे देखें, we were saying that what is the delay between one flop and another. Both the pins are being referred to as clock. But what can actually happen is that one flop is experiencing delay through this path, and the other path is experiencing delay through this path. And there are so many different sources of variations that could occur for the two flip-flops. This is called as clock uncertainty, and this needs to be accounted for in our closure analysis. So these non-idealities include clock skew, clock jitter, and variation in pulse width. Now it is very important to understand the difference between clock skew and clock jitter. Clock skew is the spatial variation in temporally equivalent clock edges. What does the statement mean? Who can clarify this cryptic statement for all of us?
Sir, it is the difference between the delta time difference between the exact moment at which we want this clock to arrive, the flop, to the actual time at which we are receiving this clock.
At different places.
At different places, Ranjit. We're talking about spatial variation. So there is one flop. So there is this circuit or that you've designed. Circuit name, a system that you designed. There is one flop that is here, another flop that is here. You assumed, okay, and the output of this is going to the input of this, let us say. There is some combinational logic in there. So you assume that clock would arrive here at time instant t0. But the very fact that these two nodes, these two flops are so far apart, the clock arriving here could be arriving at t1. This is clock skew.
Okay. Yes, sir.
Now, what is clock jitter? So clock skew is between two different flops. We're talking about spatial variation. Now, what is clock jitter?
Sir, it is within the clock generation itself. Basically, it is kind of random. My clock might have some time period, and then I see that at some points of time the clock positive edge is not coming at the expected time. It is coming at some other time.
So now we're talking about same flop. Animesh, you were saying something?
Sir, I was saying if at the same place also that there's some clock.
Now we're talking about the same flop where we say that due to let us say variations in the PLL through which you generated your clock or whatever, after some time it got heated up, or this is the wire is this clock is reaching this flop, and in between there is a set of other wires which it gets to see crosstalk with. In one cycle, there was a supportive crosstalk, and in another cycle, there was a destructive crosstalk. Huh? So between two cycles of the same flop itself, what am I seeing? The next clock edge could arrive a little early if there is constructive crosstalk, or a little late if there is destructive crosstalk. And this is called as jitter. Temporal variations. So spatial variation is skew for temporally equivalent. It was the same rising edge of the clock that we were considering. Whereas clock jitter is about same flop receiving ऊपर वाले पे चलता है. Same flop receiving clock from multiple clock. So same flop, same clock, but that clock actually getting impacted differently over different cycles now. That is clock jitter. Then there is a variation in pulse width, variation in time period, again, which could be because of some crosstalk or something like that, which could happen in the system. Crosstalk is easy to understand, therefore I'm using the word crosstalk more often. But as we just saw, there are so many other sources of variations. So that is called as clock, variation of pulse width. And all these things need to be taken care of when you do timing sign-off. So what we are talking about is that the skew is between two clock arriving at two different flops. So this could be FF1 and this could be FF2. Clock arriving at two different flops. But jitter is about clock edge arriving at a flop coming a little earlier or a little later. Okay. So what does this mean? When you have jitter, it means that this could be your T period, minimum T period, or in worst cases, your T period could actually be longer also. Are you able to see this?
Sir, in case I want to model this clock uncertainty, it is kind of increasing my setup and hold time for the worst cases.
Yes. That is why I'm talking about it right away. Now we'll go into timing analysis.
Sir?
Yes.
So the clock skew and the jitter both will be modeled under like uncertainty, clock uncertainty, that different kinds of uncertainties only.
There are different kinds of uncertainties, yes.
Okay, and so as I can see that the skew is because of the routing of the clock, because the clock is routing different paths
Okay.
exist.
Yes.
And so jitter is because of the variations, like
Temporal variations, which could be there at one point of time and may not be there at another point of time.
okay, so,
Clock skew could also be because of variations, but they are fixed variations. They could be temporal also, but fixed also.
okay.
The clock jitter is only because of temporal variations.
Okay, so sir, like for example, as you were in the uncertainty slide, you shows that there are like the one was uncertainty, there was variation due to in the source, in the device, and the temperature. These kind of variations can both lead to the skew and jitter. I mean, okay. Okay. I mean, it is not like that the skew is rated only because of the routing thing only.
No.
Okay. And sir, also I can see that like the skew, the uncertainty thing, the jitter thing, it is very unpredictable kind of thing.
Yeah.
And whether it will be there or not, I cannot definitely say.
Yeah.
But skew is more kind of deterministic. I mean, say I can still kind of.
Good. I'm so happy that you're arriving at this reduction.
So, but then how will we take in account this uncertain, the jitter thing kind of, because that would be very difficult.
We have to
Yes,
leave
sir.
the margins.
Yes, sir.
We have to leave the margins then.
Okay.
Deepank?
Sir, I just wanted to ask if the when the clock is input at a transmission gate, which is as an input to a T flip flop, So that would there would be some phase delay between the inverted clock and the normal clock. So that is counted in skew, right?
That would also be counted, and that will actually become evident in setup and hold time itself. Because
Yes,
the
sir.
inverted clock is usually generated inside the flop itself.
No, sir, I'm talking about like at the entry point of the
I
flop.
know, but you've seen the symbol of a flip-flop. There is only
Yes,
one
yes.
clock input, no? Is there a clock input for
Okay,
CKB?
okay, okay. Got it. Sorry, sorry. Got it. Got it. Got it.
CKB is an internal signal. Huh?
Okay, sir. Okay, sir. Okay, thank you.
Sir, just one more thing also want to ask. Sir, the margins that we'll be giving for the skew and the jitter, will it be different or like same only?
Let us see.
Okay, okay, sir.
So what we are essentially saying is that there could be skew. There could be skew which could be positive or negative. We are talking about two flops, and clock could be coming from this side or clock could be coming from this side. In one case, this flop will receive the clock a little earlier than this one, and in the other case, the flop will receive the clock a little later than the first one. When it receives later, it is called positive skew. When it receives earlier, it is called negative skew. Are you able to see this? Any questions?
Sir, it is about the launching of the clock, the
Yes.
point of launch.
Yeah. Okay. So now what this means is that if there is a combinational path in between them, it could happen that I have positive skew or I have negative skew, and we need to see what is the impact of skew on my path length or on the clock period. So if, for example, I have a positive skewed clock, then we realize that this combinational logic can be slightly longer. Whereas if I have a negative skew path, my combinational logic will have to be slightly smaller, shorter in length. Are you able to see this? Hello?
So why is that? So can you elaborate this?
So clock arrived here at TCLK1.
Yes, sir.
Clock arrives here at TCLK2.
Yes, sir.
Let us say combinational logic has a delay of TCOMB. If TCLK1 was the clock that would arrive at the second flop also, then what is the constraint you have to see? If the second flop also has the clock arriving at this edge only, then what is it that you have to see? You have to ensure that the delay in your combinational logic has to be less than TCLK.
Yes, sir. Yes, sir.
But since TCLK2 is arriving a little later now, I have this extra delta duration in which I can still have my combinational logic do some magic.
Yes, sir.
That is where you get some benefit.
Yes, sir. Yes.
And if it was a negative edge, you will actually have lesser time for your combinational logic.
But sir, I will be less worried about the whole time now in the negative.
Yes, you will be less worried about the whole time. So we'll just see. Let us say that I have timings like TCQ propagation, TCQ contamination, T setup, T hold, T logic contamination. What is the minimum cycle time that you can keep in this system?
T clock to Q plus T logic plus setup.
Yeah, what we say is that the next edge could be coming after a negative skew. So T minus delta should be equal to or larger than TCQ propagation delay plus setup time plus the logic delay over here. Are you able to see this?
Sir, here I may consider the negative skew.
Yes. That is the worst case, is it not?
Okay, right. Sir.
Now, let us look at the other side also. How do you, same flop, now how do you, what is the constraint that is put upon hold time? What do you want? Now over here, you will say that TCLK2 will arrive later than TCLK1. Huh? So we say that we're now looking at, what do you say? The skew to be added in the hold time requirement. We say that the contamination delay, the fastest input can come to this, and the contamination delay of this combinational logic should be greater than the hold time requirement of this flop plus delta. Are you able to see this?
So can you explain this again, sir? This whole one.
So if I say that, let us forget delta for now. Let us forget delta for now. I just want that there should be no hold time violations. What do I need to ensure? That when the next clock edge comes, TCLK2 comes, after that also, my earlier input must have remained stable. For how long? T hold long. Huh? So the delay, the minimum delay that I get from input to, let us say, from the IN pin to, let us say, this point has to be greater than T hold. Is this part clear?
So in the setup thing, when we are considering setup time constraint, we are considering two clock edges which are like T period apart. But in the whole time, we are considering the same clock edges.
Yes, whole time is always with the same clock edge.
So sir, okay. So
whole time का मतलब क्या है? Let us understand that. Whole time says that when my clock edge comes, the data from the previous or any transitions from the previous flop should not have reached me yet after T hold period. है ना? That was how we defined the hold time. Na? This was setup time and this was hold time. है ना?
yes, sir.
So we are saying that after clock edge arrives, even after that, no transition should happen until T hold.
Yes, sir.
So delays, contamination delays of this and this should be greater than T hold.
So, sir, for example, when the same clock edge arrive at both this flip-flop, so it will start processing, it will do and for the next flip-flop, I want the latching to happen, not this input to be transmitted to that.
Yes.
So, but like why in the previous slides, when we were considering the contamination, the propagation thing, you were saying that we consider for the contamination delay, we are not sure that the data will be stable or the queue will be stable or not. So why I'm not considering the propagation here and the contamination here?
What
Because
is the
then
worst case?
So, but then I don't know na ki, whether my
what
queue
is my
will be.
requirement? My requirement is no transition on the output. Should have happened. Or no transition on input should happen before hold time happens.
Yes, I mean the D pin of the next the R2 register. That
let us call this signal X. This X
Okay.
should not toggle before hold time has elapsed.
Yes, sir. Yes, sir.
है ना?
Yes, sir.
So you are now looking at the shortest delays.
Yes, sir.
That is why you use the contamination delay part.
So no, that I'm able to get. So, but for example, you also said na ki the input to be stably available at the output, that for that we consider propagation thing, because we are not sure that the data will be stable at the output Q pin of the register 1, because
Yeah.
then that only will be propagating towards that.
Let us say there are these glitches that appear. Okay.
Okay.
What is so? And let us say this is the sampling edge. What do you want? The first glitch should happen after hold time, na?
Okay, right. I mean, I don't have to concern about the stable signal, just any change in.
You do not want any transition to happen.
Okay, it
Even
could
the
be.
first glitch should not arrive, which means that I have to look at the contamination delay.
Yes, sir. Yes.
Okay.
Yes.
And here we say that we have a negative skew. Therefore, we would add delta also to the requirement.
A positive Q, I think.
Negative skew. Receiving edge is arriving early. Late. Sorry. Yes. Positive skew. Okay. The receiving edge is arriving late, so that adds to the requirement there. Okay. Is it clear till here? Friends, I need some feedback. This is very, very important concept.
Yes.
Okay. Now we look at jitter. For jitter, what we are saying is that there is a variation in clock arrival itself. Clock could arrive a little early, the clock edge could arrive a little early or a little later. So now we've added this T jitter also into the timing system. And now what would be the impact, let us say, on earliest arrival time or earliest launch time? Based on that, you will see that this is how my setup or clock period and hold requirements would change. You will see that 2 jitter would get added. One set of jitter for the launching edge and one set of jitter for the capturing edge.
Sir, in the hold only one jitter will be there.
In the hold only one jitter will be there. But if you're talking about clock period, 2 jitters will be added.
So can we say that because of jitter, the essential time period has been impacted from the source?
Can we say that because of jitter?
Jitter, the original time period of the clock was impacted.
Yes. Yeah. But you have to
And
see, you're doing sign off at one frequency. You've done the sign off, but now you need to leave the margin for jitter, because during sign off you cannot your STA tool cannot take care of these variations there, can it?
Right.
Yeah.
So this jitter is not exactly clear. I mean, how you're incorporating this.
Okay, you tell me.
Okay.
Look at this waveform.
Yes, sir.
What happens? So if you just look at the set of time wala requirement.
Yes, sir.
What could happen? Instead of clock arriving at the desired time, it arrives a little later.
Yes.
On the first flop. And for the second flop, instead of it arriving at the regular time, it arrived a little earlier. So,
Okay. Yes.
all the delays now will need to be measured from here, which is jitter later, and they should be sampled jitter duration earlier. So you have to leave margin of 2 jitter in your overall calculation.
So, but like when you were explaining jitter, you were saying that in the same flop, how MET is arriving. We were not considering 2 different flops. So I'm
Two
here.
different flops also there will be jitter, na?
Yes, sir, yes, sir. Okay. So, sir, like
No.
in my skew constraint, when I with the equation that I did in a skew constraint only, I will subtract this 2
Yes.
times the jitter.
I will
in the
add
set.
this jitter also twice.
So no, so the above equation is
It's the same equation.
okay.
Just इसको यहाँ से यहाँ के negative चीजों को यहाँ ले गए हैं. That's it.
Okay. So this
Same
is for the So this is for the setup.
Yeah.
Okay.
Okay. Similarly, for the hold, what do you see? Clock launched a little earlier because of jitter. So what happens? Now, your jitter comes. So it launched a little earlier. It launched a little earlier on the first flop, and on the second flop, it came a little later because of jitter only. है ना? So data must not arrive before P hold plus jitter now. So you have CQ plus the logic path delay minus jitter has to be greater than hold requirement plus jitter plus Q. So again, you see 2 jitter got added.
So in my the capturing flip flop, I should be considering the case of the positive skew for the whole time to be constrained.
Yeah, that is what
But
it
sir,
is.
yeah, but sir, for the starting flip flop, what exactly did you did? So that was not clear. I mean,
मतलब, we just looked at jitter.
yes sir, sir मतलब starting वाले flip flop में कैसे आप क्या देख रहे हो आप सर? मतलब इसमें edge कौन सी है?
See, it was intended to come here. It came a little earlier because of jitter. So it got launched earlier. The transitions got launched a little earlier.